start section 8.4, quadratic forms. Okay, quadratic form is a form looks like this for two variables case. Okay, quadratic forms appears in many scientific areas including mathematics, physics, economics, statistics, and image processing. Symmetric matrices play an important role in analyzing quadratic forms. That's why we have learned special properties for symmetric matrices. In this section, we study how diagonalization of symmetric matrices can be applied to analyze quadratic forms that you have learned in the multivariable calculus. First, an implicit equation in variables x, y for a quadratic curve can be expressed in this way. When you have two variables, this way. This can be written in a matrix vector form as follows, like this. This can be written in this way. If we multiply this, then you will have ax squared times cy squared and 2abxy from here. And from here, dx plus ey plus f is equal to 0. These are same, but we wrote this in matrix form. Okay? Let's think about the graph for the quadratic forms, particularly conic sections. The following are types of conic sections. Three cases: non-degenerate conic sections, and imaginary conic section, and degenerate conic section. The first case is a circle, ellipse, and parabola and hyperbola. And second case is can be shown in here. The first case. This is the typical conic sections that you have seen. This is the non-degenerate conic sections. The things, the circle, ellipse, parabola, hyperbolas, these are the ones that you have seen, and this is just one case of a quadratic form, which is called the conic sections in the standard position. Okay, this part of conic section can be written as an ellipse, which is this special case. And if you can rewrite those quadratic form in this way, if you can simplify the given quadratic form in this way, then you will have a hyperbola which looks like this. And if you can simplify a given quadratic form in this way, then you will see a parabolas in these forms. Okay, so these are all special case that you can find from a quadratic forms. Okay, the other cases. So non-degenerate conic section. So we're gonna analyze the graphs that you just saw it. Since the equation 9x squared plus 4y squared minus 144 can be written as this, like this. So the graph looks like this. Okay? This. Is it right? 이거 그림 잘못 그렸다. Okay, yeah, the first part, yeah, here, yeah, this, if we write this as 3 instead of 6, then this graph represents this ellipse. The graph of the equation is an ellipse. The equation this has a standard form like this, which is a parabola, like you see here. And this equation, y squared plus 3x equals 0, can be written in this way, this form, which is a parabola like this. So this can be drawn in here to show it. Yeah, so all the graph can be drawn using the code that I show you. The other case is degenerate conic sections. The graph of the equation x squared equals 0 is an x-axis, and the graph of x squared minus 9 is equal to 0 consists of the two horizontal lines, y is equal to 3 and y equal to minus 3. These are all degenerate conic sections, which is another special case of the quadratic forms. The graph of x squared minus y squared is equal to 0 consists of two lines, which is y equal x and y equal minus x. And the graph of x squared plus y squared is equal to 0 consists of only one point, single point, 0 and 0, the origin. So, but the graph of x squared plus y squared plus 1 is equal to 0 has no point on the xy plane. Okay. So there are many interesting cases. The graph of a quadratic form with both x squared and x terms, or both y squared and y terms, is a translation of a conic section in the standard position. If you have x squared and x terms together, then you can what? You can make a completing the square, 완전 제곱식. You can make the forms in the completing square form. So you can substitute the new axis x prime and y prime axis. Then what that means is you can translate the conic section in the standard form in that way. Okay, so the x term and y terms can be eliminated in what? A new axis, x prime, y prime. This is the example. Let us plot the graph x squared minus 2y squared minus 18x plus 4y plus 19 is equal to 0. Then by completing squares in this, we get this. Okay? What this means? If we substitute x prime as x minus 3 and y prime as y minus 1, this can be written in this way in the x prime, y prime coordinate. Okay? Okay. In the new axis, new coordinate system, this can be written as a special form that you have seen in a non-degenerate conic section case, which is a special case of the quadratic form. This equation gives the hyperbola of the standard position in the x prime, y prime coordinate plane. Hence the graph of the equation 6 is obtained by translating the hyperbola in the standard form, 3 unit along the x-axis and 1 unit along the y-axis. You can draw the graph with this code that you see here. This is a standard form, and this is a transition. 1 and 3. It's been moved 3 and 1. Yeah, moved 3 to the x-axis and 1 to the y-axis. So yeah, you can draw the so what this means is a standard form is very important. Okay, you can simplify the conic section quadratic form in a standard form by the new axis x prime y new coordinate. Now we start the same thing in a matrix form, quadratic form. The vector times matrix times the vector can be, so this can be written as this form, vector times matrix times vector, like this. This is called the quadratic form of the quadratic equation 1 with the two variables. So this quadratic form can be written in the matrix form. We call this is a quadratic form of this quadratic equation. Quadratic means the second degree. Okay, so quadratic equation, this and this are quadratic form. But the quadratic equation, this has a linear terms like minus 3x and constant term 1, so it is not a quadratic form. So this, as you see here, every terms here, x squared has x and x, two variables. Here, y squared, y, 2. And here, variables x and y, two variables. So in a quadratic form, every term has the same number of variables. Okay? But not a linear term or constant term. So quadratic form should have this form. No with constant or linear terms. So quadratic form can be written in a form like this. X transpose times AX. X transpose times matrix times the vector X. For example, this can be written in this way, and this can be written in this way as well. See the difference. Here 3 goes to the diagonal entries 1, 1. And this 7 goes to the diagonal entry 2, 2. And this minus 2 was split it as -1 and -1 here, as a half. You can write this one in this form. You will have the same form. But as you see here, this the matrix that you can find may not be a unique form, but it is always you can write in this way. If you have a CXY, then A and B goes there, and C one half of C over 2 and C over 2 can be written in this way. If you have this form here, these are all two term the quadratic forms here. So you can just rewrite everything as a D over 2, E over 2 here, F over 2 here, like this. You can write in this way. So as you see, even for the functions with 3 variables can be represented in this way. Similarly, if you have a quadratic form with 10 variables, still you can find the quadratic form of that in the same way with the 10 by 10 matrix here instead of 3 by 3. Okay? Important thing is that this is a symmetric matrix. So you can find you can do the orthogonal. You can find the orthogonally this is matrix is orthogonally diagonalizable. Okay. So we can use all the properties that we have learned in the earlier section. Here is the real definition. Let A be a symmetric matrix of order n, and X is a vector like this. Then AX, the inner product of AX and X, which is X transpose AX, that's exactly same as what you saw in here, isn't it? X transpose AX, X transpose AX, which can be written in this way, isn't it? Okay? So this quadratic form can be written as Q of X, which is inner product of AX and X. This is called a quadratic form in Rn, n-dimensional. Okay? For a quadratic form like this, Q of X is equal to X transpose AX, which is this matrix is symmetric. If you write it as a 2B, okay, here, yeah, as you see here, if you have a odd number here, all you have to do is just multiply 2 and make it as a new constant and divide it by 2 to have this form. Then you will always have a symmetric matrix A like this. We can find also normal eigenvectors V1 and V2 for this symmetric matrix corresponding to the eigenvalue lambda 1 and lambda 2. Then the matrix P is orthogonal matrix, and P orthogonally diagonalize A. That means P transpose AP is a diagonal matrix whose diagonal entries are eigenvalues lambda 1, lambda 2. If we switch lambda 1 and lambda 2, then this P can change their role. They just rotate it. If you change this lambda 1, lambda 2, then column of this P matrix just changes, because V1 and V2 are corresponding eigenvectors to the eigenvalues lambda 1 and lambda 2. Okay, so as I mentioned, since we can switch the role of V1 and V2 by switching the role of lambda 1 and lambda 2 without loss of generality, so we can always assume that determinant of A is equal to 1. Okay, that's the orthogonal matrix. So determinant can be the determinant of P can be 1 or -1. But if it is -1, just to change the first two eigenvalues, the location of it, then the columns of P matrix will be changed once. The determinant will be changed. The sign of determinant will be changed. So you can always have a matrix P, orthogonal matrix P, whose determinant is equal to 1. With this setting, we can consider P as a rotation matrix like this in R2. In R2, if we have a orthogonal matrix like this, then that's just the rotation matrix, like you have learned in the earlier chapter. Okay, here. Okay, this is just rotation in R2. Let X be a P X prime for some X prime. Then Q of X can be written in this way. Then what? With this X prime, this X, which is a PX prime, can be replaced in this way. This can be written in this way here. So P transpose AP is a diagonal matrix whose diagonal entries are eigenvalues. So that can be written in this way, which is simply simplified in this way. Okay? Hence, Q of X is a quadratic form without any cross product term in the new X prime, Y prime coordinate system. That gives the following theorem. Okay, diagonalization of a quadratic form. Here, theorem 8.4.1. Suppose a symmetric matrix A, 2 by 2 matrix, and has 2 eigenvalues, lambda and lambda 2. Then by rotating the coordinate axis, the quadratic form, this can be rewritten as follows in the new X prime, Y prime coordinate system, like this. Okay. Here, if the determinant of a P is equal to 1 and P diagonalize A, then the rotation can be obtained by P transpose X is equal to X prime, or just X is equal to PX prime, like what you saw. Okay? So every quadratic form can be written in this way in a new coordinate system with its eigenvalues, lambda 1 and lambda 2 of A, with this substitution. Here's the example. Using diagonalization of a quadratic form, determine which conic section the following quadratic equation describes. Here, what is this? Here, we only concentrate on this part. Okay, so X, so this can be written in this way, which can be written in this way. So this should be equal to 8, and this side can be written as X transpose AX, where A is the symmetric matrix. Then from this symmetric matrix, we can find the eigenvalues 2 and 4, and you can find the corresponding eigenvectors V1 and V2, and you can form orthogonal matrix P. So from this theorem, you can just write it in this way, and the new coordinate system X prime Y prime, this can be written in this way. What is this? This is an ellipse, just ellipse, in the new X prime Y prime coordinate. Okay, so then what will be the shape of this one in the ordinary XY coordinate? So in that case, we need the matrix P. We have to find P. Find the corresponding eigenvectors V1 and V2, and the normalized eigenvector V1 and V2, and form an orthogonal matrix P whose column vectors are this. Then P looks like this, which is this, and P transpose should be this one. Okay, P transpose is this should be same values. Yeah, this comes from like this. Anyway, we have a P matrix here. Then the X prime Y prime coordinate axes are obtained by rotating the XY axis to X prime and Y prime axis. So we are going back to from here to here. So what is this? What will be the rotation? We have X prime is a P transpose X, isn't it? X prime is a P transpose X. What that means is we rotated the XY axis 45 degree clockwise. So XY axis has been minus 45 degree. So minus 45 degree from that direction, like this. Minus 4. So X prime comes from here to here, and Y moves from here to here for the 45 degree, like this. So this is the ellipse of this shape in a new axis and the old axis, original axis X and Y. So all you have to do worry is finding eigenvalues and corresponding eigenvectors and normalized eigenvectors to form a matrix P, and use this substitution. X prime is equal to P transpose X. So if P transpose is a matrix, the rotation matrix from the 45 degree from the counterclockwise, and the P matrix is a rotation matrix of 45 degree from the on the clockwise directions. That's the whole idea. You can simulate it from this GeoGebra site. and sketch the graph of the following quadratic forms like this. Now you have the terms like this and constant. So do the same thing. You can rewrite this one as in this form with a matrix. This can be written in this way, and this quadratic equation can be written as a quadratic form plus bx minus E25 is equal to 0. So now what you concentrated on this quadratic form part. From here, you can find the eigenvalues of this matrix 25 and 50, and find the corresponding also normal eigenvectors V1 and V2, form a matrix P whose column vectors are V1 and V2 like this. Then we use the rotation with this substitution x is equal to px prime, which means x prime is equal to p transpose x, and we have p x transpose ax can be written in this way by with this, and do the same substitution for x to get the linear term in x prime y prime axis. So the original one can be replaced by this part minus this part, and minus 25 is equal to 0. This can be what next? We can adopt the completing squares on this to simplify in this way, isn't it? Completing square. So we delete the x term with the completing square like this. Then with the new axis. Okay. Anyway, so by the completing square, we can write in this way. This was done with the substitution involving this orthogonal matrix P with this. Therefore, the equation 12, this can be represented as an ellipse in a new x double prime y double prime coordinate system like this. Isn't it? This can be written in this way. So this is what? An ellipse in a new coordinate x double prime y double prime. And you draw that one first in a new axis, and what that means is then you move back 1 unit on x-axis and rotate the arc tangent 3/4 to the clockwise, then the counterclockwise, because you are going back to here to xy axis to draw the graph that you saw in here. The important thing is drawing this and do the resubstitute to go back to from this coordinate to this x prime y prime coordinate, and then original xy coordinate. That's the things. That's the steps that you do it. Last, surface in three-dimensional space. Suppose you have this form: g is equal to ax square plus 2bxy plus cy square. Now you have 3 variables here. Okay. After diagonalization, we can have this: g is equal to lambda 1 x prime square plus lambda 2 y prime square, like this. In a rotated x prime y prime g coordinate system. In a new coordinate system, this can be written in this way. This enables us to identify the graph of the equation in R3 easily. Here, if both lambda and lambda 2 are positive, then graph of the equation 14 is a paraboloid, opening upward. If both lambda and lambda 2 are negative, then the graph is a paraboloid opening the downward like this B. Since the horizontal cross-section of each paraboloid is an ellipse, if we cut it, you will see the ellipse. Okay? Cross-section of this paraboloid with this plane, then you will have ellipse here and here. Next, if both lambda 1 and lambda 2 are non-zero but have different signs, not same sign, then the graph looks like a saddle in A, is called the hyperbolic paraboloid like this. If lambda 1 and lambda 2 has different signs, then it looks like this. This is called the hyperbolic paraboloid. if one of lambda 1 and lambda 2 is 0, then the graph is parabolic cylinder like this. When you have two eigenvalues and one of them is 0, then this simplified in this way. We call that is a parabolic cylinder. So these are the things that you have seen in the multivariable calculus, isn't it? So this situation can be analyzed with the eigenvalues of that symmetric matrix. That's the whole idea. Example 7 shows the following. The graph of a following equation is an elliptic paraboloid, and sketchy is cross-section at g is equal to 50. Okay, you have this. You can write this in a matrix form, as a quadratic form, like this. Then this matrix has the eigenvalues and corresponding eigenvectors. From there, we can find the orthogonal matrix P from the eigenvalues of this, from the eigenvectors corresponding to the eigenvalues of this matrix. Since eigenvalues are 25 and 50, as you found it already, so this form can be simplified in this way, in a new x prime, y prime, g coordinate. What this means is you have two positive eigenvalues. So it's a paraboloid. When g is equal to 50, then we have what? Ellipse. We have ellipse. That's the answers. Okay, we continue the analyzation. Okay. So okay, this equation represents the elliptic paraboloid in x prime, y prime, g coordinate system. And note, this x prime, y prime coordinate system is obtained by rotating the xy coordinate by angle theta counterclockwise. Hence, in x is equal to px prime, p is given in this way. Okay, actually this is what you have here, and p here. So from here, theta counterclockwise, rotated. So theta is an arctangent 3 over 4 from here. So now we sketch the cross section of the equation at g is equal to 50. Then just this substitute g is equal to 50 into the equation. Then we have this. So this is an ellipse, and a new coordinate system. Has been changed, has been rotated with this angle, the counterclockwise, like this. So you can draw the graph in the new axis, which was translated this much of angle to the counterclockwise. We can do this whole process with this code. Find from this quadratic form. We find the eigenvalue of that symmetric matrix, find the corresponding eigenvectors, and then use the Gram-Schmidt social normalization process. Actually, we don't need it. Just normalize those two vectors, and then finding orthogonal matrix. And with those orthogonal matrix, we just draw the graph and the original graph. Could draw two graphs in the two different axes together with this. That's the end of section 8.5, and section 8.5 is the application of the quadratic forms. Here, you will see my lecture from this web address, and you will see my answers and the extra code for this. And here, you can. Okay, let's check that from this web address. This is a quadratic form that I made with my student a couple of years ago. From here, you will see the explanation of the conic sections and the more details, and also how to draw the graphs of the quadratic form, and how to find the eigenvalues, and what's the shape of it. And if we give the different variables, then you will see the different forms and different graphs here, and you will check what's the shape of it. And also from here, you will see how you can eliminate the cross product terms like xy and yg and etc. to have the diagonal form like this. And this also can be done in here, so you can check the eigenvalues, eigenvectors, and diagonalize, orthogonally diagonalize the things. And this things has been simplified there. And also the inertia of quadratic forms are given, and applications which include the Hessian matrix that gives you the whether it is a local minimum, local maximum, or a saddle point for a critical point, and this all computations can be done. So if you give functions, then you can find the critical numbers, critical point, and also the property nature of those critical points. If you change these functions here, then you will. If you change the functions here, then you will see the different values. And this is yeah, positive, definite, semi-definite, and those are the things that which comes in these sections. And all these are the examples that I have simulated from the section 8.6, and this shows how this.
Arm in the axolotl finds himself at the origin.
The good explanation on the application of conic sections, and yeah, we made. So yeah, anyway, yeah, this code will help you in that sense. What else? Special case of Hermitian matrix and other exercises, and there are some exercise problems that you can check it, but that's an optional, so you don't have to go through it. These are the problems that I taught to my student, and we made the code to check the answer, whether our answers was right or not with this code. And I think this address will give you plenty of information on this, more than the book can have. And next, you will do the singularity composition and Schur's theorem and normal matrices. Any questions?